Hi, my name is Ivash Berezivsky, and this is the video for my final project for Digital Forensics CS6963. My final project is to make it easier for digital forensics investigators to quickly analyze network data when presented with a large amount of potentially arbitrary data that is hard to parse and visualize. This project idea was born out of the Nitroba case assignment. While investigating that case, I found it cumbersome to analyze the PCAP data with tools like Wireshark, grep, and TCP flow. I wanted a way to quickly visualize the data or extract pertinent information quickly and easily relate it to other data points. PCAP data is rich with related connection data, user behaviors, and can be used to establish intent. For example, source and destination information, the host name, the actual data sent, and the time sent can be related and plotted in various ways. While this is a broad topic, I would like to make a tool that is extensible while keeping the scope of the project within reason. My first milestone was to create a chart that plotted search queries by IP over time. I chose this because it is important for digital investigators to establish a timeline and intent. My first approach was to use the data from TCP flow to extract the desired information from the PCAP data. This proved to be somewhat limiting, and I moved to parsing PCAP data directly. I did leave the TCP flow script there for interested parties. As a note, it does run much faster and could be useful if the PCAP files are sufficiently large. I also produced another chart which plots HTTP requests, the GET requests, to actual hosts. This can be used to quickly view a browsing history from the PCAP data from source IPs. For the visualization layer, I used the JavaScript D3 library to produce the charts. It provides an easily maintainable and extensible display layer. It is very efficient and runs on all modern browsers. This will make it easy for contributors to use the open source graphing library and the many provided examples to produce new data plots or new graph styles for the data that they are interested in. I'm now going to go over the code for my final project. I'm going to start with the Python parser that parses the PCAP data. This uses the library SCAPI to actually load and parse the PCAP data, and it uses another module that attaches to SCAPI called SCAPI HTTP, which allows me to extract the HTTP requests and responses and reconstruct those TCP flows from the PCAP data. So I'm able to get the HTTP request response and the actual data passed along if need be. This is similar to what the TCP flow library does. So kind of just starting, we'll start off in the main method down here at the bottom. Here are some of the options you can start the script with. Since it uses D3 JavaScript library for charting, I have a simple web structure here that to actually run and execute the program, you'd want to be in a web browser to view. So here are some options to start a web browser, to specify a port in case the port is taken, and to also specify the name of the JSON data that you're going to output from your PCAP data. I think it's very important to name the data different each time because the actual parsing of the PCAP data can take a long while depending on how big the PCAP file is, and you wouldn't want to overwrite the default JSON. So specifying a new name helps. So just some error checking here to ensure that we're in a directory. You can specify one PCAP file, or you can specify a directory, and the directory can contain one PCAP file or can contain many PCAP files. Another tip for this is to split your PCAP file up by time. I have a command I can show you how to run that will do that. I'll go over that in execution, but that helps break the data up and ensures that your program doesn't overflow your memory. So here I'm just keeping an account of the amount of files. I'm walking the OS directory. I'm grabbing the names of all the files, and I'm trying to open them with the scapi read pcap command with each file. And then for each file, I'm going to build the output, which we'll go to that method now. That's up here is the build output method, and that takes a grouping of packets, and it loops through each packet inside that groups of packet, and it uses the SCAPI HTTP method has layer to check if it has an HTTP request layer. If it does have an HTTP request layer, then it captures that layer and it pulls the path attribute out of that layer, and that's how I get the actual get command with the search terms in it. I then check to make sure that there's a search term in that get path, and if there is, I continue. And I essentially look for the search term inside of that GET request. I did develop my own regex to do this, but after some research and some thinking, I went and actually looked at how Bulk Extractor does its regex, and I augmented that one. They're not exactly the same, but I augmented that one to work with mine, as it is a little bit more. It works a little bit better than the one I developed did, and that also works for. I checked with Google, Bing, and Yahoo search engines. It extracts that search data and then essentially replaces the plus sign that gets appended in between each word, makes a space, and then cleans up any HTML entities that were in that search term. I then take my output dictionary that I'm making and I append the attributes that I pulled from this PCAP data to this this dictionary. And so I'm grabbing the time and I'm formatting it so it's human readable. I'm getting the destination MAC from the IP layer. I'm getting the destination MAC from the Ethernet layer. I'm getting the IP from the IP layer, and I'm getting the host from the HTTP request layer, and then I'm grabbing the parsed search data. This is the space here that if you wanted to capture more data, would make it very easy to add attributes here and pull the information from whatever layer you wish. If you wanted to not look at HTTP requests and you want to capture all layers, you could do that. You would just need to add, at this point, you would not do a checker for HTTP request, and you would essentially just build this data point for every single packet that came through. I chose not to do that to keep my data refined and to keep it small and only produce the data that I'm interested in. That's the HTTP request data. So I did that for to keep everything like compact and small. And this is sort of the power of this, is that you can decide to augment your data. You can make a huge data set and go off of that, or you can make a small data set of what you're looking for and make it easily parsable and easier to visualize. So that builds the output, and it's pretty easy to add these layers. These are not. It's just attribute value pairs. So you just do P, IP. You can go from any of the network layers provided by the PCAP data. So that's super helpful. So then after I build the output, I continue my count. I write some information to the command line to let the user know that something is happening. And then at the end, I open up the output file that was presented as the arguments, and I use the added or give it's part of the Python core library, the JSON library, and I just dump my created dictionary into the out file, and I throw some more info to the command line in case they decided to start a HTTP server or not. And then if they did, then I'll actually start the HTTP server for them and tell them where to go get their information from. So that's the PCAP parse Python file. I also, again, as I mentioned in the introduction, left the TCP flow parse Python file in, and that does a similar execution. Everything is in the main execution, but what happens here is you build the TCP flow yourself with a TCP flow command, and then you point this script at that directory from that TCP flow. Again, you can do any of the same options as before, starting the server or specifying the file name. And this will essentially go through every single file in that TCP flow directory, and it's going to look through every single file and every single line in the file, and it's going to go find the regex to look for the GET request and the search terms, and it's going to pull those out, and then it's going to append these. I'm not currently capturing the host here. That would be not too difficult to do. You would just need to specify another line here and create a regex to look for the host name after the search name in that file, and then use a regex to pull that out. Again, I moved away from this approach because you don't get access to the other network layer data, like the Ethernet frame or the IP frame. You get some access to that via the file name, and that's what these are doing. These are pulling out the time and the destination IP and the source IP, but I don't believe there's a way to get like the MAC address from the TCP flow data or any of the other any of the other type of information. I know you can get the port and the IPs and the time, but I believe that's about it. So these regexes just pull those from the file name produced by TCP flow. So that's what these are doing. They're grabbing from the file name, they're looking at the file path, and they're pulling out that information and creating the data. So this works for search terms and works for connections as well, for IP-based connections. But it won't give you the host name. So moving on, so after you do that, a JSON file is produced, and I'm using the Natroba JSON file as an example, and this is the JSON file that gets produced. Data is empty because data is just the search terms. You could have pulled all the HTTP request data and stuck it here if you wanted, but I just left it empty unless I had a search term. So I know one of the search terms here is how to. So that would be an example of a search term getting added in and used. So, and it tells you the destination, source, Google, and it gives you all this information. So what ends up happening is you would run an HTTP server in this folder, and it would take you and automatically load the index.html, which does some things. Essentially what this does is presents an opening screen, allows you to specify a data file name that you want to look at. So you can look at any of the data file names you've created in the past. And then it essentially uses the query string parameter on the URL to pass that data, to get that data and to pass it along. So this is essentially to ensure that you're at the right port and to look at whatever custom file name that you wanted to look at. So you can, say you've ran this a bunch of times and you want to go back and look at some of your other JSON files, like the JSON file from the M57 case, or a JSON file, any other sample JSON file you want. That was index. And index essentially points you to the chart HTML, which specifies the links to the other charts that I created. Again, this creates the links with the custom file name and port here. Uses some regex to pull that out of the URL. Not too complicated. Not super complicated stuff here. Just essentially stitching the web framework together so you can kind of click through and get to your charts. If you were to create new charts, this is where you would come and add them. You'd add a new link here, and you would specify the link and create a new essential endpoint for your link, so your chart would show up. So I'll go into the search chart now. So this is saying, okay, well, we're going to look for the search chart and search in XML with file names and with the file name. So we'll go over there. So search, we'll go to index.html, and this is the index for the actual chart page. So since these charts are created via SVG, they don't actually have much HTML body. The only thing in the body here is the overlay, which is going to eventually show all of the information when you hover over the data point. So that's the only thing that's actually here. The rest gets appended at runtime. There's a CSS file, but that's not super interesting either. That's just some styling, not too interesting. So let's move into the JS. I used the examples on the D3 site pretty extensively. I can show you those examples. This is some examples, but a lot of them have a very similar code structure. They give you code for all the examples, which is great, and they also have a pretty similar code structure, and D3 is kind of organized the same way. So you see a lot of similarities with the way I create accesses and stuff like that with these codes and some of the colors I use and things like that. So that's kind of in here, sort of speckled throughout. I have some links provided about the specific charts I went after. So essentially, this just pulls the file name from the URL up top here. This grabs the port. This sets up the margins and size for my chart. This is going to parse the date and make the date create, and it can easily parses the data out into information I can actually use and display. This sets the scale, the time scale for the x-axis. So essentially, D3 has has a great API and handles things like time and amounts and other either numerical data or ordinal data to make creating axes and scaling axes and creating charts very easy. So all I had to do here was just to create an X scale. I'm saying it's going to be a time scale, and the range is going to be so the size of the scale is going to be from 0 to a little bit smaller than my width. And then I'm going to actually set the axis later. This function here calculates the Y position for where my search term is actually going to show up. So it essentially is ensuring that the two search terms don't overlap. So as I'm plotting search terms down my chart, a lot of times people make searches very close together, so if they're within a second or 2 seconds of each other. This function essentially stops those search terms from sitting on top of each other to make them readable. So here I'm actually orienting the x-axis. I'm saying you're at the bottom, and there's going to be 12 information tick points across the x-axis. And that's it. There's no y-axis in the search chart because I'm not plotting anything against the y-axis. You'll see when I go over the execution. Here's the initial SVG is created, and I'll get into the D3 engine a little bit here. Essentially, D3, this is saying select the body element, append an SVG to the body element, and a lot of D3 stuff looks exactly the same. It has a very set way of doing things. I'm set the width and the height on the SVG here, and I'm going to append an SVG group element, and I'm going to set the attribute transform, and I'm going to move that group element to my margin left and to my margin top. And this is where I actually get the data. So I use the D3 JSON function, and I point it at the local host, the port, and the file name that I'm looking at, and essentially either return error or data. And I'm saying for each data item, if the data item isn't empty, so I only want to grab the data items that have search terms in like a populated item. So you'll notice if I go here, I only want the data items that actually have information. So these data items, because I don't want to plot this entire file. I only want to plot the search terms out of it. So I was back here. So I'm collecting data. So here I'm getting data, and I'm adding that data to the actual d.date object. I'm saying here, grab the date, parse the time out, and that's where this parse time method is. Here I'm grabbing the data and making it readable. I'm now going to set up the min and max values for my x-axis. So I'm saying grab the lowest date. So grab the date, grab the date closer to 1970 and use that as my min value, and grab the greatest date in the domain and set it to my max value, and then I'm going to set the domain of my actual x-axis to the min value to the max value. So I'm going to scale and create the data so that when I produce my chart, it's going to go from the minimum time to the maximum time of the actual PCAP file. I'm then going to use the SVG object I created here, and I'm going to append another group element, and this group element is just the x-axis. I'm then going to append some text to the x-axis. I append the text date time to the x-axis, and I also append the actual full range of the PCAP data, or the full range of the search terms to the chart as well. So these two, you'll see, I'm just appending some text, so you'll see the text date time at the bottom of the chart, and then you'll see the text range with the two values, and that is going to be a little bit closer to the top of the chart on the x value to make it readable. Now what I'm going to do, and this is a little confusing for D3, this is how D3 handles data. I'm going to select all of the search classes, which don't exist yet, and I'm going to add data to each one, and I'm going to enter them. So what this does is it says select all of the things, and if they don't exist, create an empty array. And then for each data point you find here, create this element and enter the data into it. So that's what's happening. So I'm basically going to create a node for every single search term that I have here. I'm then going to go, okay, I'm going to take that selection and I'm going to append some text to it. And the text I'm going to append is the actual search data. So I'm going to set the attribute search, I'm going to set the class, so I know it's the class attribute. I'm sorry, yeah, the class attribute. I'm going to set its x position, and I'm essentially going to use the x function, which is defined here, which will return me the position that this belongs on the x-axis. This is the power of D3. This here is returning a function that allows me to get x and y data depending on which axis I want to be at from this scale function that I just made. So this is sort of the power. It does all of this for you. So here I'm getting the x value, and I'm using the date because the date is the x value, and here I'm calculating the y value, and that's where I use that calculate y function that essentially ensures that the two search terms don't collide with each other. And then here I'm setting the transform. So what this is doing is this is actually rotating the text to a 45-degree angle so it's easily readable. Vertical text isn't super easy to read, so I kind of offset it at a 45-degree angle. And this is essentially doing that. I then actually set the text attribute to the data, which would be the search term that the person looked for. I then take that search term and I also create an SVG line, and I essentially create a line that attaches it back to the x-axis. And the reason I do this is because it gets a little confusing to try to figure out where on the x-axis the search term actually happened when there's a lot of search terms close together. So these lines kind of clearly delineate where each search term is. I then create a little bit of I have a mouse over effect here, and I adopted this from this visualization here, which is, I think, potentially a great visualization for network connections, but it's soccer players. But it's essentially the mouse over effect here. I'm just borrowing some of the idea to create the mouse over effect. So essentially, I'm creating that overlay which we saw in the index.html, and I'm adding all of the data to it. I'm just appending data. I'm appending all the data from my JSON file to that. And then I'm either showing it on mouse out, I'm hiding it, and on mouse in, I'm showing it. So that's the chart.js. And I'll show you this running during the execution phase. And then let's go to the other chart that I created. I'm only going to go over the code base for one of them because the other one is just switching the data up. I also created a denogram chart, and that's based on this chart here. And this is what I use to show the connection data. So there's going to be like a connection route, and then each IP here is going to be represented by a node, and then each one of those nodes will then show the connection to the host. And I'll show you what that chart looks like in a second. But here's the code to create that chart. The same beginning to do some, capture the file name import. Again, initial chart setting up. This is initializing the chart, creating the diagonals, creating the clusters, and this denogram chart is a chart that's actually again provided as a D3 like base chart. So a lot of this stuff to create these lines and to do these connections is actually provided by D3. The D3 engine just does that. So the only thing I need to do is get the data in a correct mapping and then customize the connections any way I want. So and essentially, this is setting up the clusters, the diagonals, the nodes, and the lines, and the initial SVG. So that just initializes the chart. I'm going to go over these functions in a little bit. I'm going to come back to those. So essentially, I come in, and this little piece of this little switch here is essentially creating the chart height based on the amount of nodes we have. So depending on how many nodes you have, this chart can get real tall or very small. So if some of the sample data I had was only like 8 connections, that was very small. I didn't want a very large chart. So this sort of sets the height of that chart depending on how many nodes you have. So the first thing I do is I initialize a chart, which I showed the function for that, and then I do this thing. I take the data, which is the same data I was using before, and I quote unquote fix the data. And what this is doing is this is going through and it's taking the data that I produced in the PCAP and making it into something that this chart knows how to read. This knows how to read like source to connection. The PCAP data doesn't necessarily give me the data based on source and connection. It gives me the data based on like just all the connections. So what this does is this goes in and this grabs all the source matches. So it looks for every IP that could potentially be a source, and it creates those data elements. And essentially what I'm doing here is I'm creating a brand new JSON data object based on my other JSON data object. So this is going to go and grab all of the potential source IPs. It's then going to look through all of those source IPs and get their destination matches. So it's going to go, okay, find me all the destinations for all of these source IPs. And it goes through and grabs all of those and creates the data. And essentially like pushes all of the destination data into those JSON feeds. And then this fixed data is what's calling the get source message and get destination message. Sets up a parent node and sets up the children, and then creates a new sort of connections data plot. And what this looks like is it's going to look something like this. It's going to say connections here. It's going to show me all of the source IPs here, here, and wherever else here. And then it's going to show me all of their host destinations here, 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 and here. And essentially by fixing the data, this allowed me to make sure all of the source IPs, all of their destination nodes all got grouped under the correct source IP, because that's not how it's represented here. You'll notice these are all the same source IP, but they're all their own data points. Essentially took all of these data points and collapsed them into one source with many destinations. So after we fix the data, now this chart knows how to read that data, and I create the nodes, which are these circles, and I create the links, which are these lines here. And I essentially create those using the built-in D3 API. I take all the links, I create a path. We went over how the data and enter works. I create a path for each one of those links, and I create the diagonal, that's these lines. I then capture all the nodes, and I move them all into their appropriate positions based on their dy and dx functions, which we kind of went the last time. I turn them into circles. This code is heavily taken or heavily augmented from this code here. You'll see that looks the same. A lot of this looks the same. So I essentially used. You'll notice I have a lot more code here. I eventually used this as a starting point and built my graph off of that. And I create the circles, I append the text, and you'll see here I'm grabbing the d.name, which is the host name, so I'm getting the host name and I'm appending that. And then I'm creating the same mouse over effect as I did last time to create the sort of rollover effect. And again, and that's pretty much all for this chart. It's a lot of this is built into the base dendrogram chart. And here's the index.html, which looks a lot like the chart index.html, and the CSS will look a lot like the chart CSS. Not a lot of interesting stuff there. And the other dendrogram chart, again, is another dendrogram chart, but this one's based on MAC addresses. I'm not going to go too far into that. It's very similar to the IP dendrogram chart. And that is the code. That's walking through all the code, and next we'll move on to execution. I'll now go over the execution for my final project. I will start with showing the PCAP parse and using the Nitroba PCAP data as sample data. It is good to break the PCAP file up due to Scapy's read PCAP file function, which tries to load all of the PCAP data into memory. This can be problematic if you have a very large PCAP file, say 500 megabytes. It'll try to load all 500 of those megabytes into memory and try to kind of maintain this PCAP data structure. That's a problem, as a lot of times the operating system will shut a program down for trying to use too much memory. So what you can do is you can split up the PCAP using Wireshark's edit cap command and break it up based on to a certain time and for every amount of seconds. So this will break all the PCAP data up to this time, which is like 2 days ago, and for increments of 60 seconds. So we're going to do that on the Nitroba PCAP, and that's going to output the PCAP data to a directory. So let's create a directory for that. And then we're going to this command, and the name here can be anything. It doesn't matter. It creates names based off that name. And here we'll point it at the directory we just created. And this would be the input the PCAP file, which is I have stored under here. And that'll do every 6 seconds, so let that run. That'll be pretty quick. And essentially what that does is that creates a bunch of PCAP files, as we talked about. I am then going to run the main command. I'm just going off of my README file here. And essentially going to point that at where the PCAP data we created was. And pick a name for our JSON, which I'll call video JSON, and what we want to do is start a server and set it at this port. And so this is beginning to parse the files. It broke into 263 files. Depending on how you set that time, it could be more or less files. And I will come back when this is done. It shouldn't take too long. And we're back. And you'll notice here it's finished executing and provides us a link to the URL. We'll copy that link, and it's saying it's serving on 000 at port 9001. So we'll navigate there in our browser. And you'll notice that it auto-populates the data field name for us. We'll submit that, and we'll check out our search graph. And there's our search graph. And here you'll see the range. So from Tuesday, July 22nd, 2008 to Tuesday, July 22nd, 2008 to 6:04 in the morning from 4:47. You'll notice all of the search terms here are all parsed out against the x-axis timeline. And if you hover over any of these search terms, you'll notice that it pulls the rest of the information for you along with the time, the search term, the host, the source IP, destination IP, source MAC, and destination MAC. You'll see that here as well. And if you hover over any one of these, it'll parse all that out for you and let you know when that term is actually made. So let's go back. This also produced, off that same data set, we can look at the connections via IP, and that produces the connections via IP. So you'll notice here it starts with the connections node, and looks like there's two main IPs that were sending HTTP requests. This 168.192, and hovering over will give you some more details about that. And 168.1.64 as well. And these are all the hosts that they connected to. And if the host name was unable to resolve, it'll give you the IP that the host name that was in a part of the request. So you can see here, hovering over any of these also gives you information such as the time that they connected to it, the host, the source IP, destination IP, source MAC, and destination MAC. I know specifically in this case they were looking for the will self-destruct, so there's that. We can see that information, the time that they visited that site, the host, the source IP, destination IP, and it's just searchable right here in the browser because they're just text nodes. And you can look at any of the other sort of hosts that either of these IPs have visited. I also produced the same chart, but based on MAC address, so it's telling you the MAC because IPs can be forged. It's less likely you're going to have a forged MAC, I believe. So this is just out by MAC address, and it shows you the hosts based on the MAC. So that is an example of the Nitroba. I also have data here from the M57 case that was given to us in the midterm. I have that already done here as m57.json, so I can actually just go in and put that in, since it's in the same source directory here that my server is running in. I can go put my m57.json in and submit that, and it'll quickly create me the charts for the M57 data. So here, quantum patent, I can see when that was searched. Carmaxed, Eraser, JS Patch. These are the search terms extracted from just this PCAP. There's a lot of PCAP data for that project. I just took one of the larger ones, one of the like 500 megabyte ones, and parsed through that. And we'll go ahead and look at the connection data. And here's all the connection data. And this is really interesting. They actually have more source IPs here making requests. So you'll see actually 2, 3 large source IPs. And this will kind of 4 actually. We'll show you. This kind of goes over how much data this can handle and how quickly it can handle it. It would be pretty easy for this to maybe map all the connection nodes if you want, but we'll talk about that in the next section. But yeah, so here's all the hosts going out for this request as well. So that's all by the connections via IP chart. And again, same thing, connections by MAC, and produces these charts very quickly. And again, hovering over these will give you information regarding each of these individual connections as you hover over them. And then one of the other sample data I was given was by the professor, and I've named that 215. It's just the unique number that was attached to that. So here's another one, and we can look at the search terms, and here's some coordinate data. So here's the search terms and when they were created. Looks like he was looking for the best lunch in New York City at 3/25/2013 at 1654. And we can again look at the connections that were made from this request. It looks like this was taken and there's only one IP address that was going out, and here's all of the hosts that IP address was connecting to and the times that they were connecting. So that is that. Now I'm going to cancel that and show. So if you hadn't done it all from the command line, you can just run the script without any of the optional parameters, and in that case you could just run the Python simple HTTP server and put it on port, say 9002, and just run it there. And then if you go there, it'll give you similar thing. It'll say data.json is the default data name, but again here you can just go in and specify the name of any of the JSON files that you had created, like here's the m57.json, and it'll give you all of those searches again. So you can kind of do this, and you can do any of the JSON data that you had created in the past. Second, I'll go over the TCP flow parse and how to use that. So if you go to the README, you'll notice that you need to run this TCP flow command first. So let's run that. We'll just call it output directory, and we'll use the same Nitroba PCAP data. So we're going to use from our PCAP data, we're going to use the Nitroba, and it's called output directory. And you'll see how much faster this runs compared to the other one, my other script, essentially because of the SCAPI read function taking quite a long time. So here I'm running TCP Python. I'm running the parse. I'm saying look at the output directory and call the data TCP flow _ data. I'm going to run that. It's going to run super quick, and you can again specify the server and port here if you want. I chose not to because I already have. I can just go run one really quick here. So Python -m simple HTTP server, and we'll put it on 9002 just to make sure, just to show a different one each time. So that's running there. We should be able to navigate to localhost 9003. That's not running. Oh, 9002, excuse me. Go to 9002, and we called it TCP flow. I'll just pull it from there so you can see where I'm getting this information from. JSON, and again here we'll get the search terms out from the data, and that's running from the TCP flow command. So lastly, I'd like to go over some of the future potential uses for this tool and kind of other thoughts and ideas that I've had. First, I'll start off with the other potential data set that you could use. So my data set I'm using is currently pretty small. It's only looking at the HTTP requests because I thought that was a really good piece of information to look at. It really had a lot of it was like user intent because they have to do something to cause that request to happen. But the script can be pretty easily augmented to capture all PCAP data and bundle that all together. And just to give you an example, this is the GitHub for the SCAPI HTTP module I'm using. And I'm just using this to show you the amount of data and the type of data you can actually pull very easily from the presented PCAP data. So here's from the Ethernet frame, here's from the IP frame. This is from the TCP frame, and this is all the data you can. Here's the HTTP request frame that I'm using to grab the host and the path. You can also there's also an HTTP response frame, depending. So that's all the connections coming back. So that'll give you the response if you want to look at that, and it actually will give you the data. So you can connect the response, and you can get the HTML data and potentially do things like either extract that data or use the D3 engine to create those web pages, or potentially extract the images out and have the D3 engine sort of show all the images side by side. There's a lot of things you can do there by having this data, images or requests or HTML pages. So this is just the wealth of data you can get to from there. So I'd also like to go over some other charts I saw that were really interesting and kind of just go over some of the examples that I grabbed off of the D3 charting library just to kind of show you why I chose this charting library and how extensible it is. So here's an example of a chart that shows like connections, and it actually color coordinates the incoming and outgoing connections. So as you hover over, it has green and red connections, and it's showing you the incoming and outgoing connections. But this chart is for programming package libraries like import dependencies, but this could easily be augmented to do connection data. So this is one example of a chart I found interesting. And again, all of these charts come with all of the code in line for them. Here's another chart for if you want to do like a full connection map, like you want to map all the ARP requests out or some of the other protocols out, you could definitely do this. This is a similar song network, so it's a little different, but you see how easily you can kind of come in here and just plot this data and filter it. So here's some songs. You can imagine this being HTTP connections and seeing which nodes are connecting to which nodes. And here we're going to sort by the most popular and click, and I'll show you all the connections. The next chart example I have would be like an enhancement to my current dendrogram chart, but this is, if you have an overwhelming amount of data, you can, D3 allows pretty easy transformations. You can come in here, you can look around, you can collapse nodes that have lots of information. So you can come in here, you can collapse these nodes and say, I'm really only interested in these, these four or whatever, and kind of look around, and I'm only interested in connections from here. So this would be like an augmentation to my current dendrogram chart if the data set grew and got bigger and bigger. You can see how this charting library really makes this easy to do and super flexible. And the last one I put in kind of for fun. It's a word cloud. Somebody mentioned search word clouds. So this is crawling a website and looking for the most common words. I'm gonna just do the Sci4 site for fun here. But this is another chart that can be easily augmented with my current search term chart to show you the most commonly searched for terms. So that's going to wait, and it's going to load. And I guess forensics is a word that's used pretty often on the Sci4 site. So just a word chart. But yeah, I foresee many examples just by going to the D3.js. You just go to their site, and you can see lots of beautiful charts, lots of examples. All the code for all of these charts is given. You just go to the example site here, and they have charts for everything. They have mapping charts, so if you want to map connections by geolocation, you can do something like this. They have all kinds of beautiful charts you can use, and with the code provided, so you can get a good idea and figure out how to get your data to work with these charts. And that's all, and I'd like to thank you for watching my video for my final project in digital forensics.